Hey, welcome back. This is now 10.1 in Math 0965. We are going to work with radical expressions and functions. So basically, this process will be undoing a perfect square. So for example, you know the perfect squares now, like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, etc. Right? So we're going to kind of go in the opposite direction with, and that's the square root will do that. Okay, so basically, the square root of 1 will be 1. The square root of 4 then is 2. So you can kind of see if I took the square root of this number, I get what they call the base over here. Okay, so if you take the square root of 9, you're going to end up with 3. So it's kind of like you're asking yourself the question, what times what equals the thing inside the square root? So in this case, a 3. One weird thing about the way I write my square roots is I do put this little kind of hook at the end of it. You don't see that a lot, I guess. It just tells the reader where the square root symbol ends. And I think it helps a lot when I'm writing math and when I'm reading other people's math. So I put it in there. Okay, so let's take a look here. Square roots. And so, there's two sort of what they call inverse processes. Squaring something. So if I take like 5 and square it, I get 25. Just continuing on with the chart above. Another example then, squaring 6 will give me 36. And the sort of inverse operation is going to be the square root. Okay. There's some issues though, and we have to talk about the issues here. Anyways, so the square going in the reverse kind of direction, if you take the 25 and take the square root, it'll give you back the base, which is 5. So just basically repeating what I've said already. And if you take the 36 and take its square root, you'll just get the 6 back. Okay. So what is the issue that I've kind of alluded to? It comes up when you introduce the idea of a principal square root. Basically, notice the following phenomena. So we have 5 squared equals 25, and negative 5 squared equals 25. Okay, so when you look at the square root of 25 and you kind of are asking yourself, so we have the square root of 25. Is this actually going to be 5, like I've kind of noted over here? Or, what we just found out is kind of, it could also be negative 5. I don't really know which one it is. There's kind of like two potential outputs for this answer. And so what we'll do is just say, okay, let's just take the positive one and kind of sweep the other guy under the rug. And we'll call it the principal square root. Okay, so that's going to be kind of our understanding between us math people. So what we're getting is the positive root only in these cases. Okay. So your next question may be then. Let's cross out this other guy, so we don't want that. What happens if we actually want the negative root? Well, if we desire the negative root, we'll just put a negative in front of the square root symbol. Okay. So we'll write negative square root 25. And then when you take the square root of 25, you get the 5, and then there's that negative already in front. Okay. There's a lot of homework exercises, rightfully so. These problems are kind of easy. So once you get to MyMathLab, don't freak out. There are a lot of problems, but like I said, they're easy. Negative square root 16. That's just going to give you negative 4. Be careful, you can't take the square root of a negative. There's no two numbers that can multiply together to give you a negative, right? It's always either you're going to have a positive times a positive or a negative times a negative. In either case, it's always going to end up with a positive number. So there's no two numbers that are going to multiply together to give you negative, such that the two numbers have to be the same, right? I mean, clearly, if they were different numbers, but that's not what we're talking about, the square roots. So this guy it just turns out to not be real, and we will. You probably already have dealt with this, or we will deal with this eventually. These will be complex numbers. Okay, so not real. Erase that. Not real. Okay, let's look at some other examples. You can have fractions like 4 over 25. Let's make this the negative version. So you're thinking, what times what gives me 4 over 25? And 2 times 2 will give you the 4, and then 5 times 5 will give you the 25. Okay. Be a little careful with these square root of a sum. You can't like break it apart and say that this is equal to the square root of 144 plus the square root of 25. As a matter of fact, these two problems kind of try to bring that home, nail that factoid into your brain somehow. So the number 16, you kind of have to attack the radicals as though they're parentheses, and you have to do what's inside the parentheses before you can go do anything else. So we have to add first. So 144 plus 25 is 169. And then if you think about your list of perfect squares, hopefully you have that somewhere. 10 squared is 100. 11 squared is 121. 12 squared is 144. And then 13 squared, is 169. So then, the square root of 169 must be 13. Okay. So in number 18, it's a different answer. You have the square root of 144 plus the square root of 25. The square root of 144 is just 12, and then the square root of 25 is 5. So they're two different things, and you get two different answers here. Okay, so you have to be careful. You can't just blindly kind of do whatever you want here in the world of math. You have to follow the rules. Okay, so note that 16 and 18, they're different. Okay, the square root of a sum is not the sum of the square roots. I should force everybody to say that, but okay. So anyways, there's that. Later you'll work with these guys kind of like you work with the parabolas and graphing parabolas and that sort of thing. In particular, what I'm talking about here is the square root function. Okay, this f of x equals the square root of x. Okay, so you may recall working with parabolas. So you would have over here in the top right, maybe you would have like y equals ax squared plus bx plus c. And then you get your vertex, right? So it would be negative b over 2a, comma f of negative b over 2a. And the domain would always be all real numbers. Basically, you put anything into a polynomial, it won't hurt it. But then the range was always kind of different based off the a value. It could be like, because of you just think about the picture, right? So it starts at the vertex and then it goes up if it's a greater than 0. So you would be going from the y coordinate of f of negative b over 2a to infinity. And then if a is less than 0, you would have a sad face parabola, and that would go from negative infinity all the way up to, open parentheses, all the way up to the vertex y coordinate f of negative b over 2a. Okay, so hopefully you remember that kind of junk. Eventually we're going to be doing all that stuff with radicals. It's not as bad ultimately because there's no vertex or anything like that, but one issue will be the domain that we'll worry about. Unlike with polynomials or the parabola over on the right there, the things that you put in here are have to be positive or 0. Okay, so In particular, the domain then will be all real numbers greater than or equal to 0. So what maybe a trivial question, what is the square root of 0? You ever think about that? What times what gives you 0? Where those two things are exactly the same. Well, it's just 0, right? It's kind of weird. It's like the square root of 1 just gives you 1. Square root of 4 then goes to 2. Okay, so anyways, 0 to infinity. And of course the domain is just what the possible x values that you could put into this square root function. Okay. How do I determine the domain in general? So determining the domain. Usually we'll use inequalities. So when we're working with rational functions, we haven't talked maybe about functions too much, but we have worked with rational equations and that sort of thing. What you do when you're working with rational equations, you always take the denominator and set it equal to 0 and then solve. And basically the domain for something like that would be everything except 2. So the domain would go from negative infinity all the way up to 2, and then there would be a hole kind of in the domain, so you'd put this union symbol, and then from 2 to infinity. Okay. That would be for a rational function. So all you have to do is set it equal to 0. For here, you use inequalities. Okay, so let's take a look at number 28, where we have f of x equals the square root of x plus 2. Okay, so this turns out to be pretty simple. It's easy to forget if you're not into math all day long, right? But anyways, we could extract that x plus 2, and literally all we need to do is make sure that's greater than or equal to 0. Clearly, if it's negative, then it's not a real number, and we don't want that. Okay, so we have to kind of eliminate values that would cause negatives in the square roots. So anyways, x plus 2 needs to be greater than or equal to 0. In other words, x needs to be greater than or equal to negative 2, subtracting negative 2 on the other side. And then we need to go to our interval notations. If you've forgotten, so you can do a couple values here. We need anything that's greater than or equal to negative 2. So anything greater than is all that stuff I just shaded in, and then we use a square bracket to indicate that we can also have negative 2 equal to or greater than or equal to negative 2, right? And then for our interval notation, I just kind of borrow the square bracket, the negative 2, and then I go all the way up to positive infinity. Okay, and that would be your domain. Okay, let's look at one more. Here's 32, and then we'll look at graphing these things. So f of x equals the square root of 8 minus 2x. Okay, it's the same process. You just take whatever's inside here and set it greater than or equal to 0. Minus 2x greater than or equal to 0. Okay, I need to solve this. I'm going to add 2x to the other side, so I have 8 greater than or equal to 2x. Flip-flop sides, but you got to be a bit careful when you do that. It'll be 2x less than or equal to 8. Okay, and then I have to divide both sides by 2. So I get x less than or equal to 4. In interval notation, if you need to write that out, you don't have to. It's everything less than or equal to 4. Okay, so borrowing the notation here, I have a square bracket 4, and the other direction all the way down to negative infinity. And you always use parentheses with the infinity symbols. Okay. Okie dokie. Let's take a look at a graph of one of these characters. So we'll try number 28. I need to remind myself to do a video quiz eventually. This won't be it, but I just want to write it out so I don't forget. Let me pause the video so you're not bothered. Okay, yeah, sorry. So anyways, number 28, let's take a look at this guy. So I have f of x equals the square root of x plus 2. So first thing I'm going to do is kind of find the domain. And so I extract sort of the guts of the radical and make an inequality greater than or equal to 0. Move the 2 to the other side, so an interval So I have negative 2 here. It's everything greater than or equal to that. So the domain must be negative 2 to infinity. Okay, so I'm going to do a table of values, so x comma y values to plot, and I'm going to start at where the domain starts. So I'm going to start at negative 2, and then I'm going to be putting other values in there, and I want to be clever about it so that I don't end up with any weird non-integer values. Like if you put, okay, so first if I put negative 2 in there, I get the square root of negative 2 plus 2, which is the square root of 0, which is 0. So that one's fine. I can find that on the number line. But like a number like, well, negative 1 will work. I can put negative 1 in there, no big deal. Negative 1 plus 2 is the square root of 1. Square root of 1 is 1. But then if I try to plot 0, whatever, that's where I'm gonna skip numbers like that, right? Because that's going to be root 2, and I don't clearly know where that is. I mean, you could get a decimal approximation, but I try to avoid using my calculator when I can. So I'm going to pick strategically. So if you pick 2, positive 2, it'll work, right? Because you'll end up with the square root of 4. And you know the square root of 4 is just 2. Okay. So get a couple points, maybe one more. We'll try 7, because that will give me square root 9. And we should have enough to really do an okay plot, right? Okay, so let's try it. I'm gonna need more room in the first and fourth quadrants. So 1, 2, 3, 4, 5, 6, 7-ish, and then 1, 2, 3-ish. Okay, so negative 2, 0 is right here. And I put a nice big dot there. Negative 1, 1. 2, 2 is right here, and then 7, 3. So 1, 2, 3, 4, 5, 6, 7, 3. Then I connect the dots with and leave it with an arrowhead like that. Okay. Technically, what you have there is the positive part of the square root. There's always, I mean, if you're wondering what that shape is, the shape is basically 1/2 of a sideways facing parabola. Okay, and because we're kind of dealing with the principal square root, we don't have this other kind of red thing that I just dashed in, but I'm trying to hopefully guide you towards the direction of the square root function, and noting that what it is, it's really just a sideways facing, the top half of a sideways facing parabola. Okay, so hopefully that's clear. Anyways, there it is in all of its glory. Okay. So this principal thing is kind of annoying, and basically every once in a while I get a person in my private life that I kind of know, and they learn that I teach math, and they're going to kind of stump me with a question. and then after they give me the question and they realize they didn't stump me, because I actually know something about math, which is the result of doing math all day long. I give them this question. I like to challenge people with this question. What is the square root of x squared? And the thing is, people will always think that it's just x. Okay, but it's not, right? And we kind of have a flavor for that because of this principal square root issue thing going on here. So look, let's say that f of x is equal to the square root of x squared, and let's look at f of 4. So plugging 4 in for x, wherever I see x. And let's also look at f of negative 4. Okay, so if I plug 4 in wherever I see x, I got the square root of, let's put some, maybe, no, let's just put 4 in for x and then 4 squared, right? So we'd have the square root, if I do the insides first, for square root of 16, which is equal to 4. Okay. F of negative 4, what's that? So it's a square root, and this time I'm going to put the negative 4 in parentheses. So I get the square root of negative 4 times negative 4 is 16. So that's equal to 4. Okay. So if it was the case, if it was the case that just the square root of x squared equaled x, then it must be that the square root of 4 squared would equal 4, and the square root of negative 4 squared would equal negative 4. Okay, because you see, you're just taking whatever is being squared and plopping it as your answer. All right, so if that were true, if the square root of x squared was actually equal to x, then this would follow, but we know that doesn't follow because we just computed those answers, and the square root of negative 4 squared is not 4. Negative 4, excuse me. It's this is wrong. This is not true. This is what they call a contradiction. Okay, so a contradiction. And so what the heck is it then? Okay, so I would ask somebody, what's the square root of x squared? And they would say, they think they're smarter than me. They'll say x, and I'll say no, it's not. So what is it then? Okay, so what is the square root of x squared? It turns out to be the absolute value of x. We note the square root of x squared is actually the absolute value of x. Okay, so using this new kind of definition, then we can kind of figure out our answers, and we won't end up with that sort of red circled example here. Okay, we don't have to worry about that, because with this new definition, we note that in actuality, the square root of negative 4 squared is equal to the absolute value of negative 4, which is equal to positive 4, which is what we believe to be the answer back here. So, long story short, the square root of x squared is not x. Okay, so this is no. No. Okay. This is it. Yes. Yes. Okay, so let's go to the exercises in the book then. Hopefully I didn't beat that to death, but here's 36. I have the square root of negative 10 squared. What is the answer? So it's not negative 10, right? I can't play that game. It's going to be the absolute value of negative 10, which of course is 10. And you could do it the long way. You could say, okay, this is the square root of negative 10 times negative 10, which is 100. And then the square root of 100 would just give you 10 anyways. So you play that game numerically, but when you add in variables, you don't really know what the number is that you're dealing with. It could be a negative or it could be a positive, right? So for certain values of x, x minus 2 will be negative. For other values, x minus 2 will be positive, right? And for then other values, it'll be 0. So you don't know what you're dealing with, and in those cases, you're going to have to just leave it with an absolute value. So if you'll have then x minus 2 in absolute values. Okay. And this can be really kind of annoying, and it makes a lot of parts of math very difficult. Okay. Square root of 81 x to the 4th. So we could rewrite this as the square root of 9x squared squared. And then that would equal the absolute value, of course, of 9x squared. Anything squared is always greater than or equal to 0. So technically we don't have to write the absolute values because x squared is greater than or equal to 0. This object, 9x squared, so if you took this inequality and just multiply both sides by 9, 9x squared will be greater than or equal to 0 as well, which means you don't need the absolute values. Okay? Because you'll just be putting anything in. It's kind of like, what's the absolute value of 3? You know, it's 3. What's the absolute value of 101? It's 101. You don't need the absolute values if what you're putting in the absolute values is positive. Okay, so we can just write 9x squared. The next one is the video quiz. Video quiz. Okay, so this one we get one of our cool parabolas or quadratics. Square plus 49, and it turns out we can factor that. So it's a perfect square trinomial. So x plus 7, and then we could rewrite it square root of x plus 7 squared. Okay, so whenever you have a square root of something squared, you got to use the absolute values. So this will equal the absolute value of whatever's being squared. In this case, it's x plus 7. Okay. Okay. Let's move on to cube roots and cube root functions. That was the first that quiz. That's the first question in video homework number 5. Okay. Anyways, let's move on. Cube roots and cube root functions. Cube roots and cube root functions. Okay, the issues that we had with the square roots we won't have here. You can actually take the cube root of a negative. We don't have to worry about the absolute value stuff. So it's always a lot easier. Just in general, what is cubing something? We've already kind of dealt with this when we dealt with our slope formulas back in the day. So for example, 3 cubed is just 3 times 3 times 3, which of course is 27. 5 cubed, that does not look like a 5, but 5 cubed is 5 times 5 times, whoops, I desperately want to write a 3 again. 5 times 5 times 5, which is 125. Okay. And then doing the cube root just undoes that process. So the cube root, the cube root of 27, what we do is use the square root symbol, but then we put a little 3 in there. Okay, because the square root function technically always has a little 2. So if you look to the top there, and that square root, there's always a 2 there, but we don't usually write it. Okay, we just assume it's a 2. Okay, anyway, so the cube root of 27, then you're kind of just undoing the cubing process. So 27, cube root of 27 is just 3, and then of course the cube root of 125 will be 5. Okay. Okay, so some examples from the book, number 50, and again, you can do cube roots of negatives. That's no big deal, because you would just have a negative times a negative times a negative, which would give you a negative. So what times what times what gives you negative 64, so it has to be some negative number, and then of course it's 4. Okay, sorry, that does not look like a 3. Let's look at 54. And again, you could take cube roots of fractions. So here I have negative 8 over 125. So it's going to be a negative number. What times what times what is 8? Well, it's 2. What times what is 125? That's 5. Okay. Okay, let's look at graphing these guys. So I guess part C, graphing. And again, what we're going to do is kind of identify the domain. So we're going to call this thing f of x equals the cube root of x. And its domain this time is all real numbers. There's nothing that you can't put inside of a cube root. So the domain is kind of like the domain for the quadratics. It's just going to be from negative infinity to infinity. Okay. And then we're going to do a table of values and hopefully get a nice graph. Okay, so I'm going to start with, and I'm looking at numbers that I could take the cube of, like negative 8. Cube root of that is negative 2. What else? Negative 1, I guess. Cube root of that is negative 1. 0. What times what times what is 0? That's just 0. 1. And then 8 again. Then I can come over to my xy plane. And it looks like I gotta go 1, 2, 3, 4, 5, 6, 7, 8. 6, 7, 8, and then 1, 2, and 1, 2. Then I'll draw my dots. So -8 down 2 is about right here. -1, -1 is here, 0, 0, 1, 1, and then 8, 2. 1, 2, 3, 4, 5, 6, 7, 8, 2. And it looks like this. And this may look familiar if you know what the cube function, the x cubed function looks like, because this is just kind of the inverse of that. So if you've ever plotted y equals x cubed, you know that you would get something that looks like this. And then to get the graph of a function, which is its inverse, you just rotate it about the line y equals x. So what you end up with is basically, well, I don't want to use green. Let's use blue. You end up with the cube root function, okay, which is basically what I just graphed there. Okay, so this would be the cube root of x. Okay, so you just do a rotation about that line, y equals x. Whoops. Okay, but there it is in all of its glory. Let's look at simplifying some of these ones with variables involved. So again, this is easier because we don't have to worry about the absolute values or anything. So simplifying, just basically the cube root of anything cubed is just going to give you back that anything. Okay, so for example, number 82 from the book, we have the cube root of -125 x cubed. And of course you can rewrite that as cube root of -5x cubed. And then it's like the cube root and the cubes cancel each other out, and you're just left with -5x. Okay. Okay, we want to build up to 4th roots, 5th roots, 6th roots, 7th roots, 8th roots, etc., etc. And the way we're going to handle them is kind of classifying them with either even or odd, being even or odd, right? So anything that's a multiple of 2 is even, and if not, then it's odd. Okay, so even / odd nth roots. So n for just, 1, 2, 3, 4, 5, 6, 7, or whatever. Okay, so let's look at evaluating some of these, just in the first case. So let's look at 66. We have the 5th root of 1. So it basically just asks what times what times what times what times what is equal to 1. And those whats have to all be the same thing. And the answer, of course, is just 1. 1 times 1 times 1 times 1 times 1 equals 1. So that works. Okay, let's look at another one. Here we have the 4th root of 81. So 3 times 3 is 9, times 3 is 27, times 3, 81. Sometimes you got, 3. Sometimes you got to play around with it a little bit to kind of figure it out. Of course, your calculators can do it, but in the beginning, you want to work with doing it by hand. Please note, whenever you have an even power, you just cannot work with the negatives inside your radicals. Okay, so this is not going to be real. So 4 is even, it's divisible by 2, therefore you can't take put a negative and put it inside the root. Okay, so in general, I'll just note even root of negative is never real. Roots of negatives are not real. But odd roots of negatives work. An odd root of a negative number will be basically some other negative number. Okay, so then like 68, we have the 7th root of -1. That will work, right? Because -1 by itself 7 times will give you a negative, a -1. Okay, simplifying then when you're dealing with these general nth roots, use the square roots and the cube roots as kind of a template. So if it's an even root, you're going to have to work with, if you have like the nth root of a to the n, you're going to have to work with an absolute value, just like if you have the square root of something squared, right? And then likewise, if you have an odd root, you don't have to worry about it. So simplifying then, just as I said, if you have the nth root of something raised to the nth power, that's always just going to end up being the absolute value of a, if n is even. Okay, so maybe I should quantify that. If n is even, sorry, you have to smush that. If n then is odd, it is what it is, right? So you would have the nth root of a to the n just equaling that, whatever that a value is. Okay, so let's look at one or two of those examples, and then we can hop into MyMathLab and see what kind of horrors they have in store for us. Okay, so anyways, here we have the sixth root of y to the 6. 6 is even, so this must be the absolute value of y. There's your answer. 84, we have the cube root of -6 cubed. So 3 is odd, so this will just be -6. 86, we have the sixth root of -6 to the 6. Okay, so you need an absolute value on whatever is being raised to the 6th power, and then take the absolute value, you just get +6. Okay, let's dive in. Whoa, and look at, let's take a look. Let me sort of get these together. Okay, so I'm just going to go through a whole selection of exercises, and you can use this as reference, or you can watch along if you're really kind of confused as to what's going on. Anyways, let's take a look. Let's find the square root. Negative square root of 100. So they want the negative root, not the principal root. So you're going to end up getting negative, and then square root of 100 is just 10. Okay. This one won't work, right? The square root of a negative, no. This should be 1/4. -6/8. 0.25 is 1/4. So if you wished, you could just figure out what's the square root of 1/4. I'm sort of jumping to the answer. What times what is 1/4? It's 1/2. They want an integer or a decimal. So 1/2 is 0.5. And then -0.5. This is one of the tricky ones. So you can't take the square root of 225 minus the square root of 81. The square root of a difference is not the difference of the square roots. You have to do the difference first. So 225 minus 81, 4, boom, boom, 112, 84, 1 square root of 144, so it's going to be 12. And then, yeah, so this is then the different version. So square root of 81 minus the square root of 144. It's not the same, right? This will be 9 minus 12, which is -3. So nothing all that challenging so far. They just want you to plug numbers in. So f of 37 equals the square root of 37 minus 1, which is the square root of 36, which is 6. Okay. F of 2 is going to be the square root of 2 minus 1, which is the square root of 1, which is 1. F of 1 minus 1, 0. And then f of negative 4. That negative 4 is not going to be in the domain, right? So if we square root of negative 5, it's not real. So it's not in the domain. Okay, so that's just another one of those. That's basically just another one of those. Find the domain, so that's one where you're taking the x minus 10 and setting it greater than or equal to 0. And then they're going to want it in interval notation, so 10 to infinity. So square bracket 10 comma backslash inf. If you write backslash inf, it will give you the infinity symbol. Oh, they want a picture. The domain is 10 to infinity, so it's going to be, it's definitely going to be b. And if you don't know, you can do some test values, or maybe even draw out some of it, right? But use the domain to match it. So the only one that has a domain from 10 to infinity is b. You can see the graph is going from 10 to infinity. This graph is going from like negative 10 to negative infinity to negative 10. This one's going from like negative whatever that number is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, negative 10 to infinity. We want positive 10 to infinity. And this guy is going from negative infinity to positive 10. So the b is the only one that will work because of the domain. Find the domain again. It's another one of those. Find the domain again. It's just graphing. Square root of 2 squared is the same as square root of 4. That will just be 2. Oh, so this one is, yeah, I mean, even if you did it without the absolute value stuff, negative 8 squared is 64, and then that's just going to be 8. Negative times a negative is positive, right? Let's see what else. This one you will need the absolute value, though. So this, there is an absolute value key on your keyboard above the slash key, which is above the enter key. And then x plus 6, absolute value, and then this is another one you're going to need absolute value. So square root of 25x to the 4th is the same as the square root of 5x squared squared, and then it's going to be absolute value of 5x squared. But then that's one of those ones, because x squared is always greater than or equal to 0. 5x squared is always greater than or equal to 0. If you put anything greater than or equal to 0 in the absolute values, you just get that same thing right back. So again, it's one of these issues. What's the absolute value of 3? It's just 3. So you didn't need the absolute values, did you? So that's going to be one of those. X squared. So negative square root 64x to the 6th. So rewrite it. So 8x cubed squared. And then negative, keep carrying that over. This will be absolute value of 8x cubed. You could always pull numbers out of the absolute value, because we have a product rule for absolute values. Basically, if you have a times b, absolute value of, that's the same as the absolute value of a times the absolute value of b. And then you can simplify accordingly. So in this case, we have negative 8x cubed in absolute values. You could rewrite this as negative absolute value 8 times absolute value x cubed. And then that will be, the absolute value of 8 is what? Well, that's just 8. So you get negative 8 and then times the x cubed. Okay. Let's see if they allow the other answer. I bet they do, but I don't know. It don't seem like it's really simplified. You're not going to be able to get rid of the absolute value around the x cubed. That has to be there. Okay. Well, they let you do it that way too, so I guess either way works. Yeah, this is another absolute value, like the video quiz. Factoring it is going to be x minus 3 squared, and so it will be absolute value x minus 3. Okay. And this will be negative absolute value of x minus 7. It's almost too easy. Then some cube roots, so that would be 3. Negative 4. 4 times 4 is 16 times, yeah. Negative 1/4. Negative 3 halves. And this is just plugging in numbers. Plug and chugs. Plug and chug. 5th root of 1 is 1. 4th root is 256. Is it 6? Calcutron, where are you? It's really hard to get calculator out. 6 times 6 times 6 times 6. Oh, definitely not, huh? Jeez. How about 4 times 4 times 4 times 4? Yeah, definitely. 256. Okay, so that'd be 4. This will be negative, I guess, 3. Whoops, not real. Can't take an even powered root of a negative number. Can't take an even powered root of a negative number. Oh, and this would be negative 4. All these the same. 243. That sounds oddly familiar. Maybe it's, I guess maybe it's 3. 3 times 3 times 3 times 3 times 3. Yep, 243. What's next? This will be negative something. I guess 4. Times 4 times 4 times 4 times 4. Yeah. And then you got to carry over the negative. Okay, odd power roots, kind of just, you don't have to worry about the absolute values. Even power roots, you do have to worry about the absolute values. This will be just, it's odd, so you just get negative 9 back out. And even powered roots, absolute values necessary. Oops, it's plus 3. Oof, look at that monster. I guess that's 2. Right, 2 to the 7th is 128 maybe. Don't need the absolute values, so it would be negative 2 times x plus 4. These are plug and chugs. Okay. They want you to figure out the domain and the range. Alright, sure, let's do this. So this is 10. This will be 6 plus 10 is 16. 7 plus 10 is 17. 81 square root of is 9. 9 plus 10 is 19. Is that it? Continue. Choose the correct graph. So it's got to go from 0 to infinity, and it's starting, the y value starts out at 10. Okay, so it's A. Domain is from 0 to infinitar. 0 to \inf. And then the range is going from, you can see the y values, they start at 10 and then they just get bigger and bigger and bigger. So bracket 10 to \inf. Okay, so more of the same. We'll find the domain of this creepy looking thing. So the numerator, you can put anything in a cube root, but that denominator is a troublemaker for more than one reason. So just a reminder, the domain of a function is all real numbers except first numbers that cause division by 0, and then secondly negatives inside of even powered roots. Okay. So here there's two things to worry about. We have to make sure that 20 minus 2x is greater than or equal to 0, but then we also have to make sure that 20 minus 2x is not equal to 0. Okay. We can kill both birds with one stone just by saying finding where 20 minus 2x is strictly greater than 0, and that will fix it. Okay, so add 2x to both sides, you get 2x is less than 20, divide by 2 on both sides, so x is less than 10, and that will be our domain. So starting at negative infinity, and then anything less than 10, strictly less than, because we can't include 10 because that would cause the 0. That would be the solution to this thing, right? That would be the number that would cause the denominator to equal 0. Okay, so the domain will be everything from negative infinity all the way up to 10, but not including 10, because then you would get division by 0. Okay, so negative \inf, comma, what the heck did I do? I need a parentheses. To 10. Okay, so again, this has the same, well, there's more issues now here in this one. So firstly, square root of x minus 3 in the numerator, we have to make sure that x minus 3 is greater than or equal to 0. Secondly, then I have to make sure that for the 7 minus x in the denominator, that 7 minus x is greater than 0 and not equal to 0. So we need to find where is this thing basically greater than 0. Or if you want, you can think of it as above. First we figure out where it's greater than or equal to 0, and then kind of figure out where it's actually equal to 0. Okay, so anyways, the first part, I need to make sure x is greater than or equal to 0. And the second part, then, solving the first equation, I'll have 7 greater than or equal to x. In other words, x less than or equal to 7. The second equation just says x can't equal 7. Okay, so on our number line here, x less than or equal to 7 would be this. But we also have this restriction which says that x cannot equal 7. So we need to kind of omit that number. We need to kind of get rid of it. And so when we write our answer, it'll be negative infinity to 7, but not including 7. You need to open parentheses there. Okay, but that's not quite it, right? Because we also have this condition over from the first part. X needs to be greater than or equal to 0, and there are numbers that are not greater than or equal to 0 in this interval. Okay. So what I do usually for these kind of problems is kind of make an overlap. Here is 7, 6, 5, 4, 3, 2, 1, 0, negative 1, negative 2, and then kind of compare the sort of numbers. Okay, so from 0 to infinity, that's x greater than or equal to 0. And then down here, sort of try to make them match 1, 2, 3, 4, 5, 6, 7, and on. Whatever. I need everything basically just strictly less than 7. Okay, so that would look like this. And then what I want to do is take anything that's in both intervals, and that's going to be your domain. Those numbers will work. Okay, so basically you can't pick anything that's like out here, because what will happen there is that like a number like 10 is not going to work in this expression. Okay, we can't also, for similar reasons, use the number 7, which is right here, because if you put 7 in there, then the denominator will end up equaling 0. Okay. Likewise, you also can't put anything that's like -5, and it's because now the other expression won't work. Okay, because you put -5 in there, you get -5 minus 3 is -8. You can't take the square root of a negative. So you can only use numbers that are in both intervals. Okay, and that'll be stuff up to here, and it's this basically. It is from 0 to 7. That kind of overlap between the two, they call it the intersection, right? If you probably did a little bit with the interval notation, there were intersections and there were unions. Here we're looking for where both are true. So x minus 3 has to be greater than or equal to 0, and 7 minus x has to be greater than or equal to 0, and 7 minus x cannot equal 0. Okay, so if you put all of those, if you take the intersection of all that, you get this interval from 0 to 7. So hopefully that makes some sense. Okay, but that would be your final answer. Okay, so the domain, let's just make sure. Seems like I fumbled through that. 0 to 7, but oh no, oh no, oh no. Oh, it's 3. Oh, gosh, I'm so sorry. So this will be 3, this will be 3, this will be 3. I'm going to have to cheat a little bit. 3 to the 7. Sorry about that. Next. Oh, look at that thing. 4 through to 81 has got to be 3. So the cube root of 4 through to 81 again is 3 plus square root of 576, whatever that is. 576 square root of, whoops, 576 square root of is 24. 3 plus 24 is the cube root of 27, which is, of course, just 3. What else? Oh, some sort of square root of 20x. To estimate the speed of a car, this thing, f of x is in, please use the function f of x equals square root of 20x to estimate the speed of the car f of x in miles per hour based on length x in feet of its skid marks upon suddenly braking on dry asphalt. Motorist is involved in an accident. Police officer measures the car skid lengths to be 405 feet long. So they're saying x is 405. Estimate the speed at which the motorist is traveling before braking. If the posted speed limit is 50 miles per hour and the motorist tells the officer he was not speeding, should the officer believe him? Okay, so basically we're plugging 405 into this function. It should tell us the speed of this motorist. So let's take a look. 20 times 405 equals 8100. I want to take the square root of that. Let's get 90 miles per hour. I don't think that's the speed limit much anywhere in the Americas. If the posted speed is 50, yeah, this person is speeding. So 90 miles per hour according to this formula. Well, so should the officer believe him? No. Okay. Okay, so I think that does it for us. let me go back and do another one of these domain problems. I feel like I butchered it. It was this one. So I'll do a similar question for us. So this time I have f of x equals the square root of x minus 1 all over the square root of 7 minus x. So first I need to make sure the x minus 1 in the root in the numerator is greater than or equal to 0. So I need to make sure x is greater than or equal to 1. Then secondly, there's two things here. I need to make sure that 7 minus x is greater than or equal to 0, but also I need to make sure that 7 minus x is not equal to 0. Okay? So I need to make sure x is solving this equation. The second one, add x to both sides and then flip-flop. I need to make sure x is not 7. Okay, so getting the interval notation for both of these. In the first case, all values of x greater than or equal to 1. So here's 1, and then everything greater than or equal to. So this will be the interval from, whoops. This is x greater than or equal to 1. Let's put the other, no, let's put it up here first. So adding x to the other side and then flip-flopping the inequality, x less than or equal to 7. So if here is 7, it's everything below that. And x does not equal 7, so we have to use an open parentheses here. We can't use the closed. Okay, so that interval, x basically just less than 7, and in interval notation, this guy is negative infinity to 7 with an open parentheses. This interval is close parentheses, 1 to infinity. Okay, and then we need to find the overlap between those two, the intersection. So I will do 1 to infinity here. 1, 2, 3, 4, 5, 6, 7, 8. Right, and it's everything above. And then the other guy, 7 to infinity down here. And I know there's like a 1 right here somewhere. Okay, so the intersection are the numbers that are common to both intervals, right? So we can't include 7, so we have to kind of put an open parentheses there. But we can include this junk all the way down to the number 1, and the number 1 is in both intervals. So our domain then is going to be square bracket 1 to 7 open parentheses. Okay, hopefully that'll work this time. 1 comma 7 and parentheses, drum roll. Yay. Okay, so we'll leave it there, and thanks for watching, and we'll see you next time.